Sir, you are not audible.
Am I audible now?
Yes, sir. Yes, sir.
So I was speaking since a long time for no reason. Okay, let me start again. Since till now we have seen that we can give two types of power in a digital circuit. One, either I can give 0 or I can give 1. Now you see virtually that we have calculated two powers. That if I give 0 to the input, it consumes 2.4167 picowatt. And if I give 1 in the input, it consumes 2.730 picowatt. Now, what you assume, what is your assumption? If I give both of these, this type of full wave, how much power should it consume? What do you think? How much power should it consume? I am giving this circuit 0 and 1 together. If I calculate the average power, how much power it should consume? Any random thought on this? Anyone?
More than addition of 2.
Come again?
Whole VDD will
More
be
than
consumed.
addition of 2.
More than addition of 2 means 2.4167 plus 2.730. It means somewhere around 5.1 something or maybe 5.2 picowatt. Is it? Yes, Swati ma'am.
Yes,
You have
sir.
to see anything.
Sir, from NMOS, whatever the power, it will double it. Means it will maximum consider NMOS power.
Or you mean to say that NMOS power multiplied by 2?
Yeah.
Okay. Anyone else? Any random thought? Shivansh?
So you are saying, yes, sir, you are saying means though both NMOS and PMOS are on in that
Sir,
case.
I said that I have
sir,
given this pulse now. I have calculated for 0. I have calculated for 1. Now I am giving this pulse. Only 1 0 and only 1 1. Total this much time I'll give. 20 nanoseconds for 10 nanoseconds for 0,
at
10
the,
nanoseconds
sir,
for 1.
at the same time.
At the same time, yes.
Sir, it
This
means
I'll
at
give.
the same time the power.
I'm giving this pulse. 10 nanosecond this, 10 nanoseconds. It's a
Okay,
food
so
for
it
thought.
means the power will be zero because the PMOS and NMOS both are the own. Whatever the data which we are getting from the VDD that going to ground.
That is, but the power is being consumed, na? Ajay sir, any
I
idea?
thought
Yes, Gautam, you were saying something?
No, sir.
Okay. Let us do it and then we'll try to explain that why this happens. And whatever like thoughts we have given, it says that at most it should consume 6 picowatt, right? 6 picowatt means 6 into 10 to the power minus 12 watts. This is the maximum power it should consume. Let us see how it goes. And we'll try to explain that why it happens. To my opinion, it should be higher than this. Let us see. And it will be way higher than you have thought. We are going to give a pulse with 0 to 0.8 with 20 nanosecond period and 10 nanosecond width Since I told you that I'll be running it only once, so I'll do it for 20 nanoseconds. Okay, let us run this. Is it correct? This is what we discussed for 10 nanosecond 1, for 10 nanosecond 0. See the power consumed. It is 6.582 nanoseconds. We thought that it will be 6 into 10 raised to the power minus 12. It is 6.58 into 10 raised to the power minus 9. Means whatever we thought, it is 1000 times more. This is the power of switching power. This is like you say, this is the power of switching. That's what switching do. Let us explain why this happens. It is very important to understand, because we have seen whatever the results come, but it is very important to understand why this comes. Whenever you give 0 in a circuit, we have the circuit, why I'm making it. Okay. So whenever you give 0 from here, this turns on, this turns off. When you give 1 from here, this turns off, this turns on. We have seen this. But when you do this thing, in this case, there is one situation, which is this. In this situation, there comes a point where NMOS and PMOS both are on. When NMOS and PMOS both are on, then what will happen? Everything that starts from here will get grounded. Right? Let me show you one example of this. I'll do it a bit faster to save the time, but you please try to understand what I'm doing. I've given 1 to this so that I can assume that this is on, and then zero to this, I have made it on. Now see what happens. What is the power consumption? Spectre ended because I have by mistakenly written X here. It should be 0.8. Right? Now we'll see. Look at the power consumption. It is 11.0251 microwatt. It is 1 lakh times higher than the leakage power. Right? So what is happening? That whenever I do this switching, in this switching, there comes a time when both PMOS and NMOS get turned on, and the whole voltage gets downwards, the whole current flows this side. In this case, you will be having the maximum voltage and maximum current. This I. So V cross I becomes maximum. If I do it for the whole period, it will be in microwatts. But because it happens only in the period of switching only for a very short while, that is why your result is in nanowatt only. I hope you got the point. How many of you got this point? अगर आप इसके ऊपर कभी भी
I understand, sir.
गॉट इट, इस पर आप कभी भी अगर पल्स देंगे ना, तो पल्स देने से क्या होगा कि ये शॉर्ट सर्किट में कन्वर्ट हो जाएगा, राइट? And whenever your digital circuit gets converted into short circuit, it means that it is going to consume very high power. But since you are using it in the pulse, so it gets shorted for a very small time. But in that very small time, it consumes a lot of power. Now, I'll extend my statement. Power is such a complex case. In many cases, when you will create the circuit, you will not be able to understand that why I'm getting this much of power. And if you don't get it, it means you will not be able to resolve your circuit. You will not be able to optimize your circuit. It is very important to optimize, and you will be able to optimize only when you understand that how your circuit is behaving. Right? Now I have given a pulse over here. My pulse says that your circuit will consume the power. In this case, your circuit will consume the power here in picowatt, here in picowatt. But as your circuit gets NMOS or PMOS both get activated, your circuit will consume the power in microwatt. But microwatt for a very short while, that is why it ends up in nanowatt. Now, you please understand that if I start giving a pulse like this, if I start giving more number of clock cycles in a given period, one period is this, the other period is like this. Now, please tell me with your understanding, if I calculate the power for, see, this time is same. This is T time. This clock will consume more power or this clock will consume more power?
Second one will consume more power.
Second will consume more
Second
power.
one.
Why the second one?
So because in more cycles, the switching of NMOS and PMOS is happening.
Yes, more switching will be there. And because of more switching, there will be more number of times where PMOS and NMOS will be on collectively. And the power consumption will be very high. This thing we call in our books that if you increase the frequency of your circuit, frequency of clock, your power consumption will get high. I hope you got the point why power consumption is high when the clock is higher. Right? Whenever the clock frequency of your circuit is higher, your circuit will consume more power. And I'll show you this here only, in this simulation only. Let us see how. What is the definition of frequency? Anyone? What is the definition of frequency?
Number of cycles in 1 second.
Number of cycles per second. Now you see that this is your pulse, and if you see your pulse, we have given X anywhere. Why it is saying so? Okay, here. Now I am taking this 100 nanosecond period and checking the power consumption. How many cycles I have in this input? 1, 2, 3, 4, 5 cycles in 100 nanoseconds. I repeat, 5 cycles in 100 nanoseconds, and the power consumption is 6.5906 nanowatt. Right? Now, what I do is I increase these number of cycles in the same 100 nanosecond. How I'll do that? I'll increase the frequency. Let me make it 10 nanosecond here and 5 nanosecond here. So your frequency got doubled. Let us see that. You see, there is high frequency 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 cycles are there. And now what is the power consumption? 14.1013. Nano. The previous power consumption was 6.6 nanowatt. This is 14.1 nanowatt. You have doubled the frequency. So the frequency has the impact on your power consumption. So what are the types of power we have seen? We have seen the switching power, we have seen the short circuit power, we have seen the leakage power. Now let us reduce this frequency for once more so that we can be sure of that this has an impact. I make it 40 nanosecond and 20 nanosecond. Now we have 1, 2, 2.5 cycles here. And the power consumption is 3 nanowatt. 3.10 nanowatt. So you see, for the same period, 100 nanoseconds, when you change the frequency, your total power consumption gets changed. So whenever you make a digital circuit, what are the important points that you need to take care of? You need to take care that what is the leakage of your circuit, what is the leakage of NMOS, what is the leakage of PMOS. Second, you need to take care how much frequency is of your circuit. Whenever you test your circuit, please test your circuit, the whole circuit on the same frequency. ऐसा नहीं करना कि कहीं पर कहीं कुछ और frequency दे दिया, कहीं पर कुछ और frequency दे दिया. This will give you entirely wrong results. तीसरी चीज आपको ध्यान रखनी है that you need to see that your circuit should not get shorted anywhere. So that will actually result in very high power consumption, short circuit power, right? So these are the points that you must take care of. Now I'll show you that how the MOSFET threshold voltage and MOSFET width, two things, how they impact the power consumption. Or I'll come to these two things tomorrow. Let us see what is the theory of power consumption. And because we need to start with memory also, I need to invest at least 2-3 days to the memory. I need to save time for this also. I'll come to this rest of the part of this discussion, that what will happen if I use different threshold voltages, what will happen if I use different width of transistors, what will happen if I change the input process of this circuit. I'll see this, but before that, let us see that what theory has to talk about the power. We have seen 3 kinds of power. Let us discuss about the theory, and then we'll come back to the experiments if we'll remain with some time. My screen is visible?
Yes, sir.
Okay. So let us talk about that. What is the power? I'll share these slides with you also, don't worry. So we'll be talking about three things today. One is power and energy, second is dynamic power, and third is the static power. Now, what is the power and energy? These are the simple formulas that you all know. I have just written them for your reference and for your memory only so that you can recapitulate them. What is the instant power? Power is V cross I, PT is IT cross VT. We all know. What is the formula for energy? From 0 to T, the integration of power, right? And then what is the average power? We used to compute average power in our this cadence. So whenever you are supposed to calculate this power, you are supposed to calculate the power manually. If somebody asks you to calculate this power manually and show that you are doing the right thing, then you have to use this formula. Otherwise, somebody will say that you don't know what your computer is doing. So this is energy divided by per unit time. When I do it for, suppose I compute my power consumption for 100 nanosecond and ask my circuit to get the average of it. So it computes for average of 100 nanoseconds. So means if I compute the power for average of 20 nanoseconds or 100 nanoseconds or 30 nanoseconds, it should remain the same because it is an average power per unit time, right? Then the power in circuit elements that you all know, it is very simple that this is your DC circuit because your MOSFET works in two forms. One is your MOSFET works as a resistance. I told you that MOSFET works as a capacitor. So power consumption, initially we talked, this is I cross V, current cross voltage, this is your power consumption. Then your power consumption formula for resistance is P is, if you talk about voltage, P is equals to V cross I and V is equals to IR, right? And if you use I is equals to V by R, then P will become V cross V by R, that is V square by R. And if you start using V is equals to R cross I, then your P will become I multiplied by R, that is I square R. So there are two formulas that we use, three formulas rather. This is I cross V, then V square R by R, then I square R by R. Why he is insisting on these formula in this? Because he want to say that if I for calculation of power, if I do have only source, then you use this formula. If you have facility of knowing the resistance of your MOSFET, then you can use either this if you have voltage, and if you have current, you can use this formula. So you can use any of these formulas depending on that what all you have inputs in the circuit. Then this is the energy of a capacitor. Remember, this is not just a capacitor, this is MOS as a capacitor. So what is the formula for this is 0 to infinity integration current into voltage. This is the formula for your power, calculating the energy, integrating from 0 to T. It is integrating from 0 to infinity for the infinite time. So this becomes current I is C dV by dt, right? So it has put that, and then V dt into dt, and then meeting is supposed to end. Okay, and then this becomes C is constant, and then you get this formula 1 by 2 C VC square, and this particular formula has a very important and very specific the relation when we talk about the actual practical circuit that we will see in coming slides. Remember this formula, half of CVC square. When your circuit consumes the power, it consumes a double of it. We will see how. Now, the charging of capacitor. You want a capacitor to charge along with your inverter. What happens? What happens is like the energy is half of your CLVDD square. We have just seen, but you see that total energy drawn from supply is CLVDD square. It was meant to be half of CLVDD square, but actually it is CLVDD square. So where this half energy goes, say half of the energy from VDD is dissipated in the PMOS transistor as heat, and the other is stored in capacitor, right? ये तब है when you have zero input. Zero input will this turn on, this turns off. This becomes short circuit. From here the power will come and will charge your capacitor. Now, if power is consuming in its heat, then somebody will say, then what about input zero? In case of input zero, your if you have input one, this capacitor is charged. If this capacitor is charged, then this will be on, and this will make this go towards the ground. If it is short circuit, it will make whole the charging go towards the ground. And because this is on, this will again get heat up. So this time the energy will consumed in this transistor. That we have just discussed the power consumed. Whatever we are talking about the power consumption, it is showing as an example of charging of discharging of capacitor. Actually, this heat actually is the power consumption of your MOSFET. Then this is a switching power. Switching power is very important. You say it has calculated the formula, that is CVDD square FSW. What are the parameters? Parameter is capacitance. We were not using any capacitance in our circuit, so let us neglect this. So what we are left with, VDD into frequency, switching frequency. Now please see this very carefully. VDD into switching frequency, and VDD remains constant in your circuit. We haven't changed this VDD. This has remained constant. So what was affecting the power consumption of your circuit? Frequency, switching frequency. We have seen that in 100 nanowatt, if you use one frequency, and if you use some other frequency, which will have the more impact, obviously higher frequency will give you more power consumption. So this switching power is directly proportional to switching frequency. Why I'm showing you this slide is because you should be sure that what you are doing in your experiments is directly proportional to what you are studying in your books, so that you can see whenever you learn this in any of the simulation software. Remember, technology is not all in these tools. Technology lies in your books. You please confirm what all is given in your books matches directly with what you are getting in the output of the circuits. If you are not able to get it confirmed that whether your output is right or wrong, your mentor, supervisor, like I am teaching you, I am there, you can anytime contact me and get it confirmed that whether I'm getting the right output or not. Then there is a short circuit current. We have seen the short circuit current. It says that when a transistor switches both NMOS and PMOS network, may be momentarily on, that I told you. These are on for just a moment, and it leads to blip of short circuit current. We have seen that the current was in picowatt, and when we assumed that movement of short circuit, it came to nanowatt, means 1000 time power increment, right? Less than 10% of dynamic power in a rise fall time are comparable for input and output. We will generally ignore this component, but this component is very important when this come to momentarily on part. Basically, this particular component is computed in switching part. That is why this in itself is not taken into account, but this is counted in switching part. Then there is power dissipation of sources. What is the total power dissipation? Total power dissipation is dynamic power plus static power. Dynamic power is power of switching, means frequency, and the power of short circuit, switching of load capacitances, and short circuit current. This is your dynamic power. So whenever you are supposed to compute the dynamic power in any circuit, you please assume for whatever inputs your switching of input is there, it means those power will be in account of dynamic power. If your input is static, means DC input is there, either 0 or 1, and there is no switching in input, it means your power is static, right? If your input is in switching mode, then your power consumption is going to be dynamic anyway. If your input is constant DC source and it is not switching anywhere, it means we are talking about the static power only. Now the static power has multiple components. This is called subthreshold leakage, which is most important and it is the highest among all. This is rank 1. Second leakage is the gate leakage. And these all leakages are very minor leakages. We generally ignore them. Junction leakage and contention currents are generally ignored. These two leakages are very prominent in your circuit. When you will go to your higher classes or whenever you will be in the higher studies, the other leakages will also be important. These will be asked from you. But if you do not know about subthreshold leakage or the gate leakage, then your knowledge would be treated with a pinch of salt. So these are very important. Then we see there is a voltage of frequency. We have seen its function, the function of frequency. We'll talk about how the dynamic power can be reduced. The dynamic power can be reduced by minimizing the activity factor. I'll come to it what activity factor is. Reducing the supply voltage, that is the universal process. And then reducing the frequency, we have seen this in your simulation. We will come to it, the reducing of supply voltage. This is universally accepted technique. And tomorrow, please, koi mujhe yaad karwana. I'll show you that how reducing the supply voltage reduces the total power consumption. And that is very easy to understand. You know, P is equals to V cross I. Whatever your drain current is, if you reduce the VDD, the power will come down. So reducing the supply voltage will, or वैसे भी, if you reduce the V, the I will automatically reduce. V is directly proportional to I. If you reduce V, I will also reduce and the whole power will get reduced. So the supply voltage reduction, but supply voltage reduction has a lot of difficulties with them, right? This Zoom meeting part says we are left with less than 1 minute and we'll stop our lecture here. We'll meet tomorrow with the discussion of the remaining part of delay and the remaining part of power consumption. Thank you so much and good night for today.